I am R. Prabha, Assistant Professor in the Department of ECE, SNS College of Technology. In this video, we are going to discuss the topic on magnetic field intensity due to straight conductors for the course Electromagnetic Fields and Waves. So in the last video, we have discussed the Biot-Savart's law, magnetic field intensity and also the flux density. Today's video, we are going to discuss how to calculate the magnetic field strength using Biot-Savart's law for a straight conductor. So here the challenge is the engineers needs precise methods to calculate the magnetic fields around any current carrying conductors for circuit design, antenna systems and also the electromagnetic compatibility analysis. The real world applications for these magnetic field calculations are antenna design and optimization, power transmission systems and also electromagnetic interference analysis. So now the defined stage of design thinking gives the Biot-Savart's law core concepts. So the mathematical expression is the law relates the current element to the magnetic field which produced at any point in space, and the formula is given by dH vector is equal to ideal cross r vector by 4 pi r cube. The physical meaning of this Biot-Savart's law is each infinitesimal current element contributes to total magnetic field intensity by using vector superposition principle. So the various key variables involved are the current, which is in amperes, dl is the length of each element, r is distance from the current element, and h is the magnetic field intensity. So now the design thinking ideate stage, we are going to see how to visualize this magnetic field geometry for a current carrying conductor. So the step one is identifying the current element. We have to define the current element dl along the current path or conductor path. And next is we have to establish the position vector. So determining r vector from the current element to the field of interest. So third is we have to apply the cross product of dl cross r, that is the position vector multiplied by the current element. So finally we have to integrate all the contributions to get total magnetic field intensity. So this is the method to calculate the magnetic field intensity for current carrying conductor. So this is for the ideate stage of design thinking. So next is prototype stage. We are going to see the calculations for finite straight conductor, and the various steps involved is we have to find out the position vectors in cylindrical coordinates and applying Biot-Savart's law to each current element, integrating over the entire conductor length to sum of the total magnetic field. Next is we have to simplify by using angle substitution. So the formula is B is equal to mu naught 4 pi I by R sin phi 1 plus sin phi 2. So this is magnetic flux density B. And next is the special cases for infinite straight conductor, theta value extends to 0 degree and also 180 degree. So we get simplified result by angle substitution. We get h is equal to only I by 2 pi r. And the next is for semi-infinite conductor. So the conductor extending from origin to infinity. So one angle becomes 90 degree in this case. So for in semi-infinite conductor also the magnetic field intensity H is equal to I by 2 pi r. And now, so far we have discussed the fundamental principle of Biot-Savart's law to calculate the magnetic field intensity for current carrying conductor through integration and differential contributions. So, straight conductor formula is used and also infinite special cases like infinite semi-conductors also derived. Finally, practical applications are discussed. So the practical applications include antenna design, power system analysis, electromagnetic interference prediction for engineering systems. So summary, so far we have discussed magnetic field intensity In straight conductor, its fundamental concepts, Biot-Savart's law, calculation process, the various types and engineering applications. So we have discussed all these calculations by using design thinking stages. Thank you.